Remember in quality control that there are two kinds of mean charts. Mean charts with known variation and mean charts with unknown variation. Why do you need to care about this? Oh, because if you need to draw a mean chart, you use different formulas for the two different types. How are you supposed to know the difference? This particular question right here is a good example of mean charts with unknown variation, although it doesn't say that. Let's take a look at it. 30 samples of 16 cans each. Ooh, 30 samples, well that's interesting, of 16 cans each. I know we're gonna need that for something. That is lowercase n, the size of the sample. Anyway, are measured from a canning process while it's in control. The mean of 30, the sample means is, the mean of 30 sample means. X bar is mean, so X double bar is mean of the means. I know we're going to need this information also. 12.03. And the average range is 0.04 ounces. Capital R for range, bar for average, 0.04 is what they told us. All right, before we go any further, important concept, range. Range is the difference between the largest observation and the smallest observation in a sample. It's the smallest subtracted out of the largest. So in this particular situation, it's saying that you collect 16 cans, that's a sample, you weigh them, take the weight of the heaviest can and subtract out the weight of the lightest can. That's the range. They apparently did it 30 times. They averaged those ranges. That's the 0.04. That's how you know that this is a mean chart with unknown variation. Because what does it ask? What is the upper or lower control limits of a mean chart to monitor this canning process? If you have a problem that is asking you about drawing a mean chart and it gives you information about range, it is probably this mean chart with unknown variation. Oh, all right, fine. So that's exactly what this is. What are then those formulas? Oh, the upper control limit should be X double bar, that will be the center basically, plus A2, this mysterious factor, times the average range. The lower control limit will be calculated by X double bar minus, the only difference here is the center. You add A2 times the average range in the case of setting the upper limit. You subtract A2 times the average range in the case of setting the lower limit. I think we pretty much have everything here that we need, because 12.03, that actually is X double bar, and we were remarking on the average range was 0.04. The only thing that we're lacking is, what's this A2? In the case of mean charts with unknown variation, you need a special table. It's actually included here in the note frame. The table has been established for this situation in which you don't know the natural variation in the process. Oh, and you can see that this column right here of the table says A2. We need to retrieve the number, that last number for the formula, from this table. One thing to remember about the table is, fine, these are all A2 factors, so to speak. Which one do we retrieve? You look up the sample size. You look up the size of the sample. You never look up the number of samples or anything else. You look up the sample size. Oh, that's what we needed the n for, because in this particular case the sample size is 16. So I say, all right, the row labeled 16. In the column A2, there's this number. It says 0.21. I need that number, 0.21. I need that number, 0.21, because to answer the question, the upper control limit will be 12.03 plus 0.21. There's the number from the table, times 0.04. I did that. I got 12.0384. Might as well round it because I'm kind of running out of paper also. to 12.04. There's the upper control limit. The lower control limit, just fill in the formula again. 12.03 minus, the minus 0.21 times 0.04. That's 12.0216. I'm going to round it to 12.02. There we go. They asked for the upper and lower control limits. That is the answer to this question. Now, if you look at the next question, you realize it's about the same canning process, because it says 30 samples of 16 cans each. It's that same n equals 16 are measured from a canning process while it's in control. The mean of the mean of the means, x double bar, is that same 12.03, and the average range is that same 0.04 ounces. Oh, all right. And it's asking for upper and lower control limits also. Well, right, but so what's different about this question? This question's asking about the upper and lower control limits on the range chart. The other thing that we remember about drawing charts with unknown variation, 1, you need the special table. 2, there's actually 2 charts. There's a mean chart that you then plot future sample means, and there's a range chart that you use in the future to plot future ranges in samples. Oh, now the range chart, the limits are actually easier to calculate than any of the mean charts, because the range chart, the upper control limit is nothing more than factor D5 times the average range. There's no plus or minus or anything in here. You just need those 2 parameters. The lower control limit is equally as simple. You just need D4 and you multiply it times the average range. And of course we know, we're familiar now with this situation, the average range is 0.04 ounces. What is this and what is this? Oh, it's that other part of the table that we didn't use yet. Right? Here's where we got our A2 factor for the mean chart, but here it says range chart, D4, D5. That's where we get them. All right, our sample size is 16, so we just continue along that row and we snag these 2 numbers because we're going to need them, 0.36 and 1.64. We're going to use them because in the case of the upper control limit, it is, let's see, 1.64. That was that far right-hand column, times 0.04, that's R bar. And in the case of the lower control limit, that's the 0.36, that other column, times 0.04. So do those computations, and I get that the upper control limit on the range chart should be 0.0144 ounces. And the, that's the lower control limit, 0.0144. Thought that looked kind of small. Whereas the upper control limit, which is 1.64 times 0.04, that should work out to 0.0656.